In this video, we're going to learn the steps you need to take really when you're learning a new definition, and we'll also study how to write a rigorous mathematical definition of something that you already know well, or at least you already have a very good intuitive idea of what it should be. So, the first thing is, whenever you're working with a new definition in mathematics, you should do really 4 things. The first one, I know it's great to have an intuitive idea, that helps a lot, but in mathematics, we always need to work with the rigorous definitions. So make sure that you understand the rigorous definition well and not just the intuitive idea. After that, make sure you write some examples of objects that satisfy the definition, but it's also important to write non-examples, so examples of things that don't satisfy the definition. Because you see, if we define something and absolutely everything satisfies the definition is not very useful. So it is always good to look at things that satisfy the definition and things that don't. And try to carefully write the negation of the definition. And you will see that steps 3 and 4 usually go together. So let's take a look at the definition of increasing function. I'm sure you have an intuitive idea of what an increasing function is. It's a function whose graph goes up. Or we could say that the larger the x, the larger the f of x is. Okay, but this is not rigorous. It's a good intuition, but it's not rigorous. First of all, what do we mean when we say the larger x is, the larger f of x is? Well, that is kind of giving me an idea that I have to compare values, right? Because the larger, well, larger means that something is larger than something else. So, well, let's try to compare the values of f at 2 different points. So I pick 2 arbitrary points. I know x1 and x2. And I see that x1 and x1 is less than x2 and f of x1 is less than f of x2. So maybe we can try something like increasing means x1 less than x2, f of x1 less than f of x2, but this is really not a definition. To begin with, we have to introduce all the symbols we use. I haven't said what f is, I haven't said what x1 is, I haven't said what x2 is. So, okay, not good. Let's try again. Well, in our definition, we know that f is a function, and x and y, x1 and x2 should be arbitrary real numbers, but how arbitrary can they be? Well, let's take a look at this here, this graph. We have this function is increasing on the interval ab, but it's decreasing on the interval bc. So this means that when we're talking about increasing, the notion of a function being increasing, we might say in which interval the function is increasing. So now let's do another attempt. Let f be a function. Good, we now know what f is. We said that f is increasing on I, so we fix the problem of the interval. When x1 and x2 are in I, x1 less than x2, f of x1 less than f of x2. But this is still not a definition. Because, you see, do we mean that there exists x1 and x2 in I, such that the 2 inequalities are true? Is this for every x1 and x2 in I? Do we mean something else? What is the relationship between x1 being less than x2 and f of x1 being less than f of x2? I don't know. It is not clear. So we need to work a bit more. We have to go a bit further with this. Okay, so I'm going to give you 3 options of how to complete the definition and see if you can get the right one. So which of the following are the correct way of completing the definition of increasing function? So we have that let f be a function defined on the interval I. We say that f is increasing on I when for every x1 and x2 in I, x1 less than x2 and f of x1 is less than f of x2. Option 2, there exists x1 and x2 in I such that x1 is less than x2 and f of x1 is less than f of x2. And last but not least, that for every x1 and x2 in I, if x1 is less than x2, then f of x1 is less than f of x2. And now I invite you to pause the video and try to work out which one actually means what we want to say. So which ones means that the graph goes up, or that the larger the x is, the larger the f of x is. So try to think about it. And if you think that one of them is not the correct way of completing the definition, try to think about why. What makes it not good? What makes it wrong? Maybe it's that you know that there is a function that is not increasing that satisfies it. I don't know. Try to think about it, but please pause the video, and I'll see you back in a few minutes. Great, welcome back. I'm sure that now you have a good candidate, so let's discuss them. Okay, the first one. Well, the first one is not good. Maybe you were tempted to use this one, but there is a big problem with this one, is that no function f satisfies this. Not even a single function in the world can satisfy this one, because you see, here we're saying that for all x1 and x2, x1 is less than x2, then if x1 and x2 happen to be the same, it is impossible to have that x1 is less than x2. So the whole thing goes out of orbit. So this one cannot be correct. Now, the second option, probably you notice that this one shouldn't be right, because we're saying that there exist two numbers such that x1 is less than x2 and f of x1 is less than f of x2. But I can find a function that is not increasing that satisfies the definition. For example, if I take f of x equals x squared, this is not increasing, we know that. But it satisfies the definition because, you know, -1 is less than 2. F of -1 is 1, which is less than 4, which is f of x2. So we have a function that is not increasing that satisfies the definition. So that definition has to be wrong. And the last one is correct. It's very clear, it's very precise, and it tells me indeed that if I have x1 is less than x2, it forces f of x1 to be less than f of x2. And another equivalent way of writing option number 3 is that if x1 and x2 are in I, and x1 is less than x2, then f of x1 is less than f of x2. Okay, now we have a rigorous definition, and as I said, we need to first understand the rigorous definition. Check, we know. Now we need to check an example. Okay, simple, very boring example. The function f of x equals 2x is increasing the real numbers. Sure, yeah. So what do we need to prove? Well, first, we have the intuitive idea. It's good. So we need to check that satisfies the definition. So we need to show that for every x1 and x2 in the real numbers, x1 less than x2 implies that f of x1 is less than f of x2. Well, how do we prove this? First of all, we're starting to prove a statement that begins with a universal quantifier, so we need to fix arbitrary real numbers, x1 and x2. Then we have an implication. So, what is the implication here? Well, we need to assume the hypothesis and end up reaching the conclusion. So we're going to assume that x1 is less than x2, and we need to conclude that f of x1 is less than f of x2. Perfect. So now we need to do some manipulations in between. I have a big gap there in my proof. I need to fill it. Okay, well, I know if x1 is less than x2, if I multiply two sides of the inequality by 2, everything stays, it preserves the inequality. We're going to talk about that later when we talk about real numbers, but for now, we're good. We're going to assume that we know that from high school. So we know that 2x1 is less than 2x2, but 2x1 is f of x1, and 2x2 is f of x2. So voila! We know now that f of x1 is less than f of x2, and that completes the proof. Awesome! We've done an example of an increasing function. Now that we have an example, we need to go and take a look at a non-example. So we need to take a look at something that is not increasing. And ideally, we would like to provide a proof of why it is not increasing according to the definition and not just by looking at the graph. We know that the function f of x equals x squared is not increasing on R. And we can look at it in the graph. It's clearly not increasing on the real line. If we only take the interval 0 to infinity, it is increasing, but not as a function over the whole reals. But of course, this is not a proof. We first need to know what we mean when we say that f is not increasing on R. So to do that, we need to take a look at the negation of the definition of f is increasing on R. So we need to negate the statement for every x1 and x2 on R. If x1 is less than x2, then f of x1 is less than f of x2. So how do we negate this? Well, if we want to show that It is not true that for every pair of numbers in the reals this happens. Well, we need to just find two numbers, x1 and x2, such that it is not true that x1 less than x2 implies f of x1 is less than f of x2. Then what is the negation of x1 less than x2 implies f of x1 less than f of x2? Well, if you want, pause the video and try to think about it. Great. So now that you had time to think about it, I'm sure you got it right, but let's write it down to make sure that we're all on the same page. Well, we end up with the rexes and x1 and x2 and the real numbers such that x1 is less than x2 and f of x1 is not less than f of x2, or what's the same, that f of x1 is greater than or equal to f of x2. So now that we have the negation, we just need to check that indeed the function f of x equals x squared satisfies this. So okay, let's see. We need to prove something with an existential quantifier. So remember, giving an example is enough. So in my case, I want to take x1 equals to -2 and x2 equals to 1. So -2 is less than 1, check. And now let's see, f of -2 is equal to 4. And 4 is bigger than 1, which is f of 1. And that completes my proof of the fact that indeed the function f of x equals x squared is not increasing.